Right, welcome back Physics 30. Today's lesson is the beginning of Unit D, Nuclear Physics. And this unit is, although it can be one of the most trying one, depends on, well, people's perspective. If you really into nuclear physics or anything that involves nucleus, this is your unit. And this Unit D, to be fair, some of the Unit D section I put it at Unit C Part 2. So that's why Unit D booklet is not as big as compared to the others. Just for the heads up. All right. Let's see. So today's lesson is our first lesson. Basically, we need to understand what is nuclear physics. When people say nuclear, they think about, well, it depends, but some people may think about South Korea and North Korea because North Korea is a nuclear weapon, or how that even work, or some people may think about Simpson and then a nuclear power plant, anything like that. So basically, I generally consider nuclear physics as, instead of electron, imagine you're thinking about atomic level of physics, but mainly talk about proton and neutron. And we're going to talk about our for nature fundamental forces that we have in this universe. So number one, using the gold foil scattering experiment that was done in beginning 1900s, Rutherford and others showed that the nucleus was composed of proton and neutron. And if you guys don't remember nucleus, that's the one where at the very center, it composed of most of the density and most of the mass of that certain atom, but they're located at the center. And these quantized nuclear particles are known as nucleons. So we now use, for the mass instead of kilogram, you may see the U, because it's kind of like, you guys remember for energy notation, 1 electrovolt is equivalent of 1.60 10 to the power of negative 19 joule, because that's how much energy that can be transferred as an electrical form. Similarly, when it comes to atomic mass, we use this U, and it is about mass of the proton or neutron. I believe in the new curriculum, this was turned out to be 1.67. Have that in your mind. The charge of electron, we know it's -1. Charge of proton, +1. Neutron have no charge. When it comes to mass, proton and neutron is known to have 1 U, but electron is not close at all. The reason because is 1.99 10 to the power of negative 31 is way smaller than the one mass of proton or neutron. So we virtually kind of put it at 0. If you want to find out the ratio of it, well, why don't we just do it? 9.11 10 to the power of negative 31 divided by 1.67 10 to the power of negative 27 times by 100. It's about like 0.05% of 1 U. So that's why. Nuclear notation. Some people learn this in Science 10, and I do teach a little bit of this notation. First thing first, element symbol. You can get it from your periodic table, but number that belong on top is known as mass number. Number that belong bottom is atomic number. So atomic number is generally always smaller. Mass number is bigger because it composed of proton number plus neutron number. On the other hand, atomic number only talk about proton number only. And if you think about it, that's periodic table. Atomic number 1 is hydrogen. Atomic number 2 is helium. Atomic number 3 is lithium. it also shows the charge of nucleus. So for example, sodium 11, 25, that means I have 11 protons. And when it comes to neutron, it is 25 minus 11. So it is 14 neutron. If we're talking about atom, that should have the same number of electron for the proton, 11 electrons, something like that. But what is important is proton and neutron. So let's do a quick example. For the isotope, and we're going to talk about isotope. Actually, you know what? Let's talk about isotope first. Isotope is this. Now let's think about it. Proton number shouldn't change. Proton number is always same. Like for example, if I have proton number 1, that is always hydrogen. If I want to say, oh, there's a proton number 2 for hydrogen, that's impossible, because as soon as you have 2 proton, that's new element, that's helium. So same number of proton always belong for the same number of element. However, what is different is neutron number can be different. And whenever that happen, and let's go back to our example over here, we put that different neutron number after the element's name. So let's do this. Carbon 14. When you hear the word carbon 14, this 14 is my neutron number. So I want you to look at your periodic table. Periodic table is available at the back of your booklet, your data sheet booklet. Carbon's proton number, atomic number is 6. Then, where does that 14 go? 14 goes as a mass number. And you can identify how much proton, how much neutron, something like that. Number of proton, same as the bottom number 6. Number of neutron is mass number, which you put it, I put mass. Mass number goes after the element number, It goes 14 minus proton number 6, so you have 8 neutron number. When it comes to number of nucleon, that is combination of proton number and neutron number, so it's 14. If you talk about electron number, then it should be same as proton number if it is on atom. As soon as it becomes ion, then you gain electron or you lose electron. That's positive and negative. It is chemistry 20 and 30. Now let's go through the fundamental forces. In this universe, we have 4 fundamental forces. One is gravitational force. Second, electric force. Third and fourth is what we learn here. I believe it's not entirely given, but one is known as strong nuclear force, one is weak nuclear force. So weak nuclear force is, imagine there's a matter, proton and neutron. While you're ripping these two apart, heat energy comes in, and those are weak nuclear force. Strong nuclear force is nuclear fusion. Imagine I have proton, neutron, another proton, neutron. The one that basically bind them together is strong nuclear force, and that force is way stronger than the weak nuclear force. In fact, the weak nuclear force is whatever weaponized nuclear weapon. Strong nuclear force is basically our planet, center of our planetary system, sun, undergo that. But in any case, strong nuclear force. The proton in nucleus are very close together. So if you think about electric force perspective, they should repel. Why? Because it's proton, proton. They hate each other. But despite that, despite the fact that they both have like charges, there is another force that hold the nucleus together, and this is known as a strong nuclear force. And strong nuclear force is applied for following matters. It is attractive force, extreme attractive force that happen between a pair of nucleons. So it exists between neutron, 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 proton, proton, and proton. It is very, very short force. In fact, the distance are very short, like 10 to the power negative 15 meter, and it is the strongest force in nature. But when the distance increases, the force decreases dramatically. We are not going to go through that mathematically, but theoretically, you should know. Einstein played a huge role in nuclear physics. In fact, any physics, to be honest, modern physics. We are not talking general relativity, but everybody probably heard that E is mc squared. So I'm going to talk about that. Now, nuclear physics, before we getting into in-depth nuclear physics, one thing that you need to understand is, mass defect. So what is a mass defect? Mass defect, it's like this. The total mass of stable nucleus, we found that it's always less than sum of masses of its constituent proton and neutron. And the difference of that mass, people don't know why there's a mass difference. So every element, you need to think about this way. The total mass of proton and neutron is actually a little bit larger compared to an actual mass. So there is an error of conservation of energy and mass in here. Well, basically conservation of mass. So Einstein proposed an idea. He suggests that mass can become a source of energy. So when we found this defective mass, which is a lost mass in the nucleus, probably it is used in a different form of energy. In this case, it is used as binding energy, like strong nuclear force. So to calculate this equivalent energy from the mass defect, he suggested formula, one of the most important formula that's having come out, is mc squared. Delta M is mass defect, c is speed of light, E is energy converted from mass. So as a result, physicists introduced this mass defect and energy from it as law of conservation of mass energy, and that's specifically referring this formula that you see above there. And of course, next question is where the mass and the energy from that defective mass go. And like I kind of spoiler alerted before without warning, it is used as binding energy. The equivalent energy associated with the mass defect of the nucleus is called binding energy of the nucleus. This represents the minimum energy that must be put into nucleus in order to completely break it apart into its components, proton and neutron. It is also the energy released when proton and neutron comes together to form an atom. So we're gonna do some actual calculation. First thing first, determine the nuclear binding energy of copper-65, and we have an actual mass. So good idea to find delta M first, which is 65 proton and neutron together minus what we have, 64.928 U. That gives me my mass defect. And it turned out the difference between those is 0.072 U. And we can actually convert this into kilogram by multiply by 1.66 10 to the power of negative 27. And that's how much mass is defect. Now it says find out the nuclear binding energy, which we can use our good old Einstein theory. So it gives you 1.07568 10 to the power of negative 11 joule, which, as you may notice, energy in this unit, if you think about joule, it's gonna make your life nuts because the value is very, very small. So what we can do is convert into electrovolt. Then you have that much of electrovolt. I believe you will know, divided by a million will make it into mega electrovolt. So 67.23 mega electrovolt is my energy, or you can just say 67.2 mega electrovolt as a rounded answer. That is what I want to point it out. Now, from now on, because energy can become mass, and same thing goes mass to energy, we can identify whatever the mass that we have into an energy notation. This unit is a unique unit, MeVc square. This is actually unit of mass, but it has a condition. If it is used entirely as an energy. Because if you think about E is equal to delta mc square, if I isolate for delta m, you may notice that it's E over c square. And what do you know? In previous question, if you look at it, energy, yes, it's joule, but we can change it into EV, but that's a lot of energy, so we could convert it into mega electrovolt, right? So if you look at the unit, MeV c square, you may notice that that is equivalent of my mass in kilogram. So determine the mass energy of proton. This is fancy way of saying finding out the energy format, and we're gonna express that into mass unit. So here's what you can do. We know that E, delta mc square, and delta m is basically m of proton, assuming that entire mass is contributed to energy. Once you punch the number in, the values come out like 1.503 10 to the power negative 10 joule. And we gotta divide it by this number. Then we have that electrovolt, which divided by million, we have about 934. Is that 4 or... Let me just punch the number in. Oh, 9.39. There you go. Mega electrovolt, which you can use it as mass is equal to 939 MeV c square. Something like that. Energy and mass now can be convertible. Your to-do list is basically do any question that you see from section A, page 4, and section B, page 5. That is today's lesson.